Yeah, so want to talk a bit about some of the work we've been doing to really scale DBOS and Postgres. And this has been because our users are growing and we're seeing people running now tens of billions of workflows per month on DBOS. And that means we have to really architect it to scale and to push the limits of Postgres. So I want to talk, first we're going to talk a bit about some of the benchmarks we did. We recently had a big blog post about benchmarking DBOS and how much it scales. You might have seen it did really well in Hacker News. And I'll talk a bit about some of the optimizations we did to, to make this kind of scale possible. So I want to start with the benchmark. So we're running a benchmark to see how much DBOS scales. So we started with a huge Postgres box, so one of the biggest boxes that Amazon will let you rent. 96 cores, 280 gigs of RAM, a lot of IOPS. This is massive overkill for most workloads. We were trying to push the limits. Uh, and what we found is that with that box, you could run a lot of workflows. So running simple workflows from a large number of parallel async clients, we could push DBOS to 43,000 workflows per second, which is more than 4 billion workflows per day, hundreds of billions of workflows per month. And this is just off of a single Postgres instance. And digging into performance from a Postgres perspective, this was an extremely write-heavy workload where each workflow is performing a minimum of one insert and one update, an insert at the beginning to create the workflow record, and an update at the end to mark the workflow as completed, plus one additional write per step. And so from a Postgres perspective, this workload can scale a lot, to 43,000 workflows per second. And when it bottlenecks pretty much entirely on how fast Postgres can flush these writes to disks. So flush writes from its log to disk. So from a Postgres perspective, when you're running at 43,000 workflows per second, you have one Postgres backend doing a group commit to flush all the most recent workflows to disk, and then every other backend, every other client waiting for this group commit to finish. So yeah, at this extreme scale, to answer the question in chat, at this extreme scale, when you're running tens of thousands of workflows per second, this is a very write-heavy workload in that all of the work that DBOS is doing is writing workflow record updates to disk. So creating, every second creating 43,000 new workflow records and then updating those records when the workflows finish to complete it. And I want to stress this is an extreme workload. I think most people are actually writing workflows that do something instead of writing workflows that just spin for a few seconds and finish. And then they'll bottleneck on whatever their workflows are actually doing. But if you're just running DBOS, trying to run as many small DBOS workflows as possible, then what you'll bottleneck on is Postgres writes. And that can scale, and Postgres can handle a lot of writes. We also took a look at queues performance because I think in our experience, most people don't run workflows directly, but they enqueue workflows. And looking at queues, scalability is also great. A single queue can handle about 12,000 workflows per second. And with multiple queues, that scales up to about 31,000 workflows per second. And the reason for this graph is that with only a single queue, you get slowed down by contention on that queue, where you have hundreds of processes all trying to dequeue from the same queue at the same time. They're all locking the rows they're trying to dequeue. And if you're running enough concurrent dequeues for enough concurrent processes, above 12,000 processes per second, that contention slows down dequeuing. Of course, with multiple queues, you can spread out the load, and we end up with substantially higher performance. So I think the big takeaway we got from these benchmarks is that DBOS scales. Like with a single Postgres, you can handle several tens of thousands of workflows per second, and then if you really have a monstrous workload that requires more than that, if you're really running tens of billions of operations per day, then you can scale that horizontally by scaling Postgres. But DBOS can scale to meet just about any workload that suits it. And then to make that scale, the other thing I want to talk about is what it takes to make that scale. So what optimizations we did, or some of the interesting optimizations we did to reach that scale. Oh, so Kevin asked, what's the CPU utilization when you hit the right bottleneck? So that depends on Postgres size. On the monster box we used for benchmarking, CPU utilization was actually relatively low. And that's because it was actually relatively low. But on a smaller box, so I think it was below 20% on the monster box. But on a smaller box, you will bottleneck on CPU before you bottleneck on IOPS. So with say an this is on a 96 core machine. If you have a more reasonable sized machine, say one with 8 or 16 cores, you can still actually get tens of thousands of workflows per second. You might get 10,000 instead of 40,000, but then you'll see a CPU bottleneck instead of an IOP, instead of a write bottleneck. It's actually not an IOPS bottleneck. It's something slightly nastier than that. It's a latency bottleneck on while flushing, which can't be resolved by adding more IOPS. I can go into details of that later, but you can't add more IOPS to get around that. There are ways to get around that, but we didn't go into that because we already got a big enough number for now. And this is so a couple of the optimizations we did. The first thing we did, these are both queue optimizations because I think regular workflows are just an insert and an update from a Postgres perspective. That's relatively easy to scale. But queues are more complex because when you're doing queues at massive scale, you have hundreds of workers all trying to read from the same queues table and all trying to dequeue the same workload, the same workflows. So making that complex coordination problem scale really well and scale just as well as regular start workflows required a bit more work. So the first thing we did was fix the isolation level of the queues query. So the main dequeue query originally ran at a repeatable read isolation. And the reason for that was because queues support some global flow control parameters like global concurrency and global rate limits. And those are only safe if the queues query, if every process has the same consistent view of the state of your queues. Because if processes have inconsistent views, then it's possible for multiple processes to dequeue too many workflows and breach a rate limit or a global concurrency limit. But we also realized that the problem with repeatable read isolation is that Postgres has to do a lot of work to make sure that every process has this globally consistent view of data. And this creates a lot of contention. This causes a lot of failed queries, aborts, and retries. We realized is that for a lot of use cases, it wasn't necessary because for most of our users in their high throughput queues, they weren't actually using global flow control. They weren't using global rate limits or global concurrency limits. They were mostly using local per process concurrency limits. So we decided to heavily optimize that common case. So the first thing we did was we moved worker concurrency, and instead of tracking it through the database, which is somewhat wasteful, we just track local worker concurrency, how many workflows are running on a particular worker in that worker. So that eliminates some queries, eliminates some CPU usage. And then after doing that, we then reduced the isolation level of the dequeue query from repeatable read to read committed, specifically for queues that are only doing local flow control and not global flow control. And those two optimizations together, I think, really reduced contention in the dequeues query and was one of the key components of allowing workflows even on a single queue to scale into tens of thousands of workflows per second. Then the other optimization we did was to rebuild all of the indexes that DBOS uses. So the DBOS workflow status table has a lot of indexes because people need to do a lot of queries over it. Some of those indexes I'd say they grew organically in response to user needs. And as our customers grew, we recently went back and reevaluated those indexes to decide which ones we needed and how to make them as fast as possible to reduce the cost of index maintenance So two big optimizations we did here. First, we took many of the indexes that were designed mostly for observability, like the indexes on columns like forked from or parent workflow ID, which are infrequently used columns, and made them partial on those columns not being null. So what that means is that those indexes are still useful for observability. If you're forking, if you have a lot of child workflows, then you can use those indexes to search, for example, for what the parents of what the children of a particular workflow are. But if you're not using those features, those workflows aren't maintained. Those indexes don't have to be maintained because they're only maintained for workflows that are actually actively using those features. So we transitioned several of our observability indexes to partial indexes to make sure that they're not being used unnecessarily. Then the second optimization we did was really building an index that's narrowly tailored for the DQ query, instead of making that query share indexes with other operations. So this new index is on exactly the columns used by the Q query, Q name, status, priority created at. And what that means is that the Q query can use this index to find all the workflows on a particular queue that are in-queued and retrieve them in sorted order. And then it can pick out the ones that the workflows that it wants to dequeue. And that's much faster than what we were doing before, where we had the indexes on queue name and status, but we didn't have the sorting wasn't built into that index. So the queues query was doing a sort as part of its query plan, and that made it far more CPU heavy than it should have been. So put these together, and we're seeing much better performance for the DQ query because it's now completely indexed, and we're seeing much less index churn because far fewer indexes need to be maintained, and that gets again substantially better queues performance. Okay, so to sum it all up, Postgres fast, DBOS fast, and then keep an eye on your when to improve performance, keep an eye on your indexes and keep an eye on your isolation levels.
Any questions here? Fabian, interesting case that you had. I responded in the chat a little bit. Any other questions on the benchmarks or your own benchmark stories?
Yeah, a lot of these optimizations were released in 4.17. So if you're on 4.16, you don't have them yet. So I would definitely try them out.
And this I think what it was interesting for us also the min polling interval. I think it had also some impact there, but then I upgraded also to the wrong version, or not the latest version. Yeah, cool that it was tackled exactly in the version where I encountered the problem.
Yeah, of course, min polling interval, relaxing that will help you, of course. But with some of these new fixes, hopefully you won't need to. Yeah. Do you remember how many workers you used in the big benchmark, Peter? I realized I never asked you this. The thing that's doing 40,000 workflows per second, how many workers is that? Polling DBOS.
If I remember correctly, it was, I believe we capped out at 512 workers.
Very nice, very nice. Yeah, we have users doing more though. We have some doing thousands of workers.
DBOS will scale for more than that. But then your workers are actually doing real work. My workers were just hammering DBOS over and over again.
Yeah. Yeah, Afzal wants to know how much it cost. Oh, that's classified, Afzal.
Not, I mean, but we didn't have to. We not too much. To be clear, that's a very expensive server. That server is massive overkill for most workflows. You can actually get most of that throughput. You can get the tens of thousands of workflows per second on a much smaller RDS with far lesser cost. This was just overkill for the sake of benchmarking.
Yeah. Evan, hi Evan, good to see you. Do you recommend using worker concurrency or global concurrency, or do they need to be both configured? And yeah, like worker is the one that you need most often in the majority of the cases, because what you would do for queues is make sure that any one worker doesn't take on too many tasks. Otherwise, you OOM or crash or something like that. Global concurrency is used sometimes, but much more rarely, right? So global concurrency is something like all your workers are hitting a service, and that service can only handle so many requests per second or something like that, right? So that's why we optimized worker concurrency here, and that's the case that you need most often.